Hello everyone, my name is Saeed Mehraban. I'm an assistant professor in computer science at Tufts University. Today I'm going to present to you my recent work with my collaborator Mehrdad Tahmasbi. So we finished this project when Mehrdad was a postdoc at Tufts University, and Mehrdad is now a postdoc in ULUC. All right, so the title, this is going to be presented in STOC 2024 in Vancouver in about a few weeks. So the title is Quadratic Lower Bounds on the Approximate Stabilizer Rank. Okay, so the main question is, how hard is it to simulate quantum computation on quantum computations on classical computers? And of course, basically, this is so in terms of complexity classes, this is about the relationship between P and BQP, which BQP stands for bounded error quantum polynomial time. And of course, if we can separate the two, then we would separate complexity classes such as P and P space. And these are long-standing open questions, and this is not what we're going to do in this talk. So instead, we're going to ask a more relaxed question, namely that can we rigorously show specific simulation techniques for simulating quantum computers, and classical computers take exponential time. So before getting to the details, let me give you a short background on the quantum computing side. So quantum state is a vector in a complex Hilbert space that has unit L2 norm. So geometrically, it means it lives on a sphere. The block sphere is what you can see in this slide. You can read in detail about either of these topics in textbooks such as Nielsen Chuang, Wikipedia, on and on. So quantum operations are unitary matrices which map states that have unit L2 norm to states that have unit L2 norm. So these are unitary matrices, they're invertible. And from unitary matrices, we can talk about unitary circuits. So similar to classical circuits, we have unitary circuits that decompose an arbitrary unitary operation into sequences of gates. So we have the Born rule, which is basically the probability of getting an outcome from a quantum state is absolute square of the value of that vector, that quantum state vector in that direction. And they sum to 1 because you have unit L2 norm. Okay, so what are some of the basic quantum gates? So you have the XYZ, which is basically the Pauli operations. So they're 2 by 2. So they maneuver one qubit. So X is like naught, Y is like naught with added phase. Z is like assigning like plus minus depending on like the value of the vector being 0, 1. There's a Clifford gate set, which is the phase gate S, like Hadamard, which maps 0 to 1 plus 0, like a mixture of 0, 1, and 1 to another mixture with a minus sign on 1, and C naught, which is a classical gate that gets applied to a 2-qubit gate, to 2 qubits. And the T gate, which applies a pi over 4 phase to basically the ket 1. So similar to classical computation, we can talk about universal quantum circuits, and indeed Clifford plus T are universal. Something that we need to know is that like Paulis are also generated by Clifford. So for example, S squared is just Z, and you can as a practice generate X and Y based on, let's say, combinations of H and S. So what is basically an important tool in quantum computing is that Clifford circuits by themselves, let's say starting from the all zeros state, can be simulated efficiently. This is a well-known theorem by Gottesman and Neal. And that just means that the T gate is exactly what makes computation hard. So if you have like T gates, then you can do universal quantum computation, but without that, based on Gottesman-Neal theorem, you can simulate them on a classical computer. And what Gottesman-Neal theorem tells us is that if you start not only from the all zeros state, but from a families of quantum state known as stabilizer states, then you get let's say, easy to simulate computation. So what is a stabilizer state? So some definitions we say an operation A stabilizes a vector psi if psi is a +1 eigenvector of A. So for example, consider the Pauli. So the Paulis correspond to a group. If I add just like some phases, indeed plus minus and plus minus I. So tensor products of these Paulis, they correspond to a group. And the stabilizer states are exactly the states that are stabilized by some subgroup of the Paulis. And you can see that like basically, unless the group is abelian, because Paulis either commute or anti-commute with each other. So the case that you have elements that anti-commute, then the stabilizer subspace is trivial. So we look at the abelian subgroup. So these are stabilizer states, and there's a theorem that like stabilizer states are exactly what you get if you apply Clifford's to all zero. So then in a way, Clifford operations on a stabilizer states are easy based on like Gauss-Mendel theorem. Okay, so to give you a picture, single qubit stabilizer states are all the 6 corners of this these points in the block sphere that you saw like in a few slides ago. So for example, 0, 1 are like stabilizer states. Like for example, 0 is stabilized by Z. 1 is stabilized by minus Z, so we can, like plus is stabilized by X, and minus is stabilized by minus X, and you can do all the math like in your free time. So to see like for 1 or 2 qubit case, what are the stabilizer states and stabilizer groups, depending on which one you start first. So, but there are many other quantum states on this block sphere that are not just like a stabilizer state. So what is the situation with those? As a matter of fact, if you can start your Clifford operation based on copies like some quantum state that is not a stabilizer, namely the magic state. So for example, the T state that you can see on top left, so is like 0 plus e to the I pi over 4 1. So it's like the vector that is orthogonal to the face of this polytope, like in this picture. So this is called a magic state because using a simple gadget, which you can see on the right-hand side of the slide, you can basically simulate the effect of a T-gate. So in a way, this is called magic state teleportation. So you can teleports a T-gate based on like Clifford operation on T state. And what is important is that you only use Clifford operations in this gadget. So basically the C0, computational basis measurement, and like a phase gate. So to give you a more concrete picture, so if you have like a universal quantum computation based on Clifford and some T gates, you can always, let's say, use T states, like just single, like copies of a single qubit state, like called T. And basically you can use the gadgets that I told you to basically perform universal computation based on Clifford only operations, starting from magic state. So in that sense, they are magical. Okay, so then the question is that then how hard is it to simulate a Clifford operation if I start with some arbitrary quantum state, phi, along with like number of like the stabilizer states, such as like zeros? So the answer is that this one answer is that it depends on the stabilizer rank of phi, in the sense that I'm gonna describe in the next slide. So the stabilizer rank of a quantum state is the minimum number of stabilizer states that I can take a linear combination among them to approximate that quantum state. So an exact rank is when delta is equal to 0. Of course, exact rank is a stronger definition, but approximate rank is a more useful definition. So for example, among other results, there is a result of Brovy and Gossett from 2016 that universal quantum circuits using m number of T gates can be approximated using simulated within order delta in time that is proportional to approximate rank of m copies of t, like chi delta of like t to the m. So this number, which is a fixed number, it doesn't depend on the details of your computation. It only depends on the number of like the t states that you start with. And the proof idea is that you just take the state and decompose it into that many, let's say, terms, and use Gauss-Mennel theorem on each branch separately. Of course, there are many details that I'm hiding, but you can read the paper for the details. So we have some upper bounds, like for example, the last one I'm aware of, like is from Qasim Pashayan and Gasser, like from 2018, that stabilizer rank is exponentially large. So you would expect it to be exponentially large. Otherwise, you could simulate arbitrary quantum computations in polynomial time, if, for example, it is bounded by some polynomial time. So this talk is about the lower bound. Can we show that like the stabilizer rank is always like more than some exponential number? Okay, so what do we know? Of course, similar to any other lower bound question in theoretical computer science, you hope to prove like exponential, but the best you can do is some polynomial. So this question was studied in various works. Brody Smith Smalley in 2016 proved a square root of n lower bound on an exact rank. And recently, three works using three different mathematical ideas proved linear lower bound on the exact rank and proved basically square root of n lower bound on the approximate rank. And they use different ideas such as higher order Fourier analysis, number theory, linear algebra, but all of them stop at linear. And the main contribution of our work is to get around this bottleneck and prove quadratic lower bound, well, almost quadratic lower bound for both exact and approximate. And we use probabilistic method and quantum state synthesis. I will add some highlights on the nature of the proof technique in the end. Okay, so let me just tell you briefly about like why this might be of interest to the theoretical computer science community. Of course, we know about the P versus NP question. So the question is that can we show that NP complete? Of course, this is a large, long-standing open question, and we are not attempting to even get close to it. But we can ask other questions such as like, can we show that like NP complete problems do not have short representations within specific models? So the model that is relevant to this work is linear combination of over complete functional basis. So particularly, there's a work by Williams from CCC 2018. Sorry, there's a C missing there. So that he shows that like for any k, there is a function f that in NP such that it requires n to the k terms in any decomposition into quadratic functions. And the one question we can ask is that can you show similar results for p? Like, can you give an example of a function in p that you need better than linear, let's say, lower bound? Because I think in that work it shows a linear lower bound, like for functions in p. And indeed, as a byproduct of our results, like we show that like there indeed exists a function in p that requires quadratic. And we should also mention that we use an observation by Peleg, Spelka, and Volk, like from 2022. They say that if they can prove quadratic lower bound, then they can improve this result. And then our example exactly fits into like what they observed there. And there are outstanding open questions such as like quadratic uncertainty principle, like for example, the AND function can be proved that like it requires exponential terms in quadratic phases, and these are interesting questions that this field is about. So okay, so let me tell you about like the proof technique. So we have three steps. The first step is that approximate stabilizer rank for random state is exponentially large, and random state is like from this distribution called Haar measure. And second, we use a result of Low, Kliushnikov, and Sheffer from 2018 that an arbitrary state, including a random state, can be prepared using 2 to the n over 2 number of t-gates. And it's important because the t-gates are exactly the gates that matter to us. And naively, you would expect that you need like 2 to the n number of t-gates, but this, I would say, surprising results of LKS from 2018 shows us that you can get a quadratic improvement. And this is indeed like one of the core elements of this proof in our result also. And the third step is that we use the teleportation idea that we told you to say something about the stabilizer rank of T state. So as you can see, it's very simple, but of course you need to figure out a lot of details, like putting all of them together, but the outline of the proof is not too difficult to digest. So the first result, so to give you a bit more detail, so if you have a random state that is sampled from the Harmonic over n qubits, then you can show that with high probability it has near maximal like stabilizer rank, because of course you can decompose any state into a 2 to the n number of like bases, but for a random state up to polynomial, like that's also in a way tight. So the proof idea is that if you take any combination of R stabilizer states, if R is less than 2 to the n divided by some polynomial, then you can use concentration of measure to show that like the concentrations are on the small value. Then we use union bound over all possible ways you can select these vectors. So the second step is we just recite the theorem by LKS that if you start with all zeros state over n qubits, then you can construct any quantum state using 2 to the n over 2 number of t gates, but many ancillas and many Clifford gates. So particularly you will be using exponentially many ancilla, but like for us, that is okay because so long the Clifford gates do not change the stabilizer rank. So the picture should have been a very small circuit on the left and a very tall like circuit on the right. So it's like it's vastly larger than the left hand side circuit. So I hope you can use your imagination for that. So yeah, like that is like kind of precision. So lambda is exponentially large, like 2 to the n over 2. Let's say T gates is so basically the third step is basically you use teleportation to just teleport in a way like bring all the T gates to and replace them with T states, and Clifford only computation do not change your stabilizer rank. But what is important is to show that the teleportation gadget, because it involves like measurement on and on, it does not change the stabilizer rank, and that is one of the technical elements in the paper. But putting it all together is going to be just giving you the value, just like you use 2 to the n over 2 the gates to get 2 to the n stabilizer rank, then you just use some change of variable, get quadratic. Okay, so that's, as I told you, it was simple to imagine like what are the steps, but let me just tell you some discussion and open questions. So first, what we define is like we can think about this ensemble of states that require a small number of T gates and have high stabilizer rank, some pseudo-random definition. So so basically the two ideas to go beyond the quadratic value is just to define this pseudo-random ensemble and like prove some their existence for like better parameters. And the second idea is that if we can show that like if you have two random states and take their tensor product, then their stabilizer rank of the tensor product is slightly more than basically basically each of them in a way. For very modest parameters such as exponentially small delta and so on, then we get actually all the way to exponential lower bounds if all the details work out. So of course there are many details to Consider we can show this for doubly exponential small delta, an epsilon being as large as like 1, but going to 1 over 2 to the n delta, that's a big step. Okay, so the second thing I want to say is that like, what can we understand about this proof technique? So we know that like all the previous results stop at linear lower bound. So what do they have in common? Is that they use some property of the lowest tabular rank states. But what we use here is that like basically we get lower bound through an upper bound. Let's say problem. So in particular, upper bound on the state synthesis problem gives you a lower bound. So it's like something about similar to like going around like some natural proof technique for this problem, but I'm not an expert in this, and we hope to understand these connections better. And let me know if you have ideas, or I hope to have conversations with you during the workshop. So I think I'll stop here for the interest of time. I hope you have a great day. Sorry, let me stop sharing.